Hello everyone, and welcome to Dr. Carminati's YouTube channel. I'm so excited to have you here today as we dive into a fascinating phenomenon that sounds straight out of science fiction. What is quantum tunneling? This topic takes us deep into the heart of quantum mechanics, and I can't wait to explore its mysteries with you. Suppose you love uncovering the secrets of the universe. In that case, I'd love to hear from you. Share your thoughts in the comments, suggest ideas for future videos, give this video a like, and hit that subscribe button to join our community of curious minds. Let's embark on this incredible journey together and discover the magic of quantum tunneling. To understand quantum tunneling, we first need to enter the strange and wonderful world of quantum mechanics. Quantum mechanics explores the behavior of the tiniest building blocks of reality, particles like electrons, protons, and photons. Unlike the everyday world where things follow predictable rules, quantum mechanics reveals a realm of probabilities and oddities. Particles can act like waves, exist in multiple states simultaneously, and even influence each other across vast distances. These peculiarities challenge our intuition, and quantum tunneling is among the most surprising and impactful. In the classical world, the one we experience daily, objects behave in ways we can easily predict. If you roll a ball toward a hill, it either has enough energy to climb over the mountain, or it stops and rolls back. The hill acts as a barrier, and the ball can't pass through it without enough energy to overcome it. Classical physics tells us that barriers are solid and impenetrable unless an object has the energy to surmount them. Quantum mechanics, however, flips this idea on its head. It introduces the possibility that particles can tunnel through barriers they shouldn't be able to cross. Let's dive into what this means and how it happens. Quantum tunneling describes a phenomenon where a particle passes through a barrier that, according to classical physics, it doesn't have enough energy to overcome. Imagine a particle, like an electron, approaching a wall of energy, a barrier too high to climb over. In the classical world, the electron would bounce back, unable to proceed. But in the quantum world, the electron has a small chance of appearing on the other side of the barrier, as if it dug a tunnel through the wall, hence the name quantum tunneling. This happens because of a fundamental principle in quantum mechanics, the wave-particle duality. Particles like electrons don't just act like tiny marbles, they also behave like waves. When you describe an electron as a wave, you use a wave function, which tells you the probability of finding the electron in a particular place. The wave function doesn't stop abruptly at a barrier. Instead, it extends slightly into and beyond it, even if the electron doesn't have enough energy to cross. This means there's a small probability that the electron can leak through the barrier and appear on the other side. Let's paint a picture to make this clearer. Imagine a child bouncing a ball against a brick wall. The ball always bounces back in classical physics. It can't go through the wall. Imagine the ball as an electron and the wall as an energy barrier. In quantum mechanics, the electron's wave function stretches through the wall, and there's a chance the electron will suddenly appear on the other side, as if it magically tunneled through. The thinner and lower the barrier, the higher the chance of tunneling. This defies our everyday experience, but it's a well-established reality in the quantum world. To dig deeper, let's explore the science that makes quantum tunneling possible. The key lies in the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle states that we can't know both a particle's position and momentum with perfect precision at the same time. If we know the position very well, the momentum becomes uncertain and vice versa. This uncertainty allows particles to behave in impossible ways, like borrowing energy for a brief moment to cross a barrier. When an electron approaches an energy barrier, its wave function doesn't vanish at the barrier's edge. Instead, the wave function decays exponentially inside the barrier, meaning The probability of finding the electron decreases as you move through the barrier. However, if the barrier isn't too thick, the wave function doesn't drop to zero. It still has a small value on the other side. This tiny probability means the electron can sometimes tunnel through, appearing on the far side without ever having the energy to climb over the barrier. Mathematically, physicists describe this using the Schrödinger equation, which governs how quantum systems evolve. The equation shows that a particle's wave function can penetrate barriers, and the likelihood of tunneling depends on the barrier's width and height and the particle's energy. For example, a thin barrier allows more tunneling than a thick one, and a particle with energy close to the barrier's height has a better chance of tunneling than one with much lower energy. Quantum tunneling isn't just a theoretical curiosity, it plays a crucial role in nature and technology. Let's start with nature. One of the most stunning examples occurs in the sun. The sun produces energy through nuclear fusion, where hydrogen nuclei combine to form helium, releasing massive amounts of energy. For fusion to happen, the hydrogen nuclei must overcome a strong repulsive force, the Coulomb barrier, caused by their positive charges. Classically, the nuclei in the sun don't have enough energy to get close enough for fusion to occur. But quantum tunneling allows a small fraction of these nuclei to tunnel through the barrier, enabling fusion and powering the sun. Without tunneling, stars wouldn't shine, and life on Earth wouldn't exist. Closer to home, tunneling drives processes in our bodies. Enzymes, the proteins that speed up chemical reactions in cells, often rely on tunneling to work efficiently. For example, when enzymes help transfer protons during reactions, the protons sometimes tunnel through energy barriers rather than jumping over them. This makes reactions happen much faster than classical physics would predict, allowing life to function at the speed it does. In technology, quantum tunneling powers some of our most important devices. Take the Scanning Tunneling Microscope, STM, for instance. This tool lets scientists image surfaces at the atomic level by measuring the tunneling of electrons between a sharp tip and a sample. Electrons tunnel through the tiny gap when the tip hovers just above the surface, creating a measurable current. By mapping this current, the STM reveals the positions of individual atoms, revolutionizing nanotechnology. Tunneling also plays a role in modern electronics. In flash memory, used in USB drives and SSDs, electrons tunnel through a thin insulating layer to store data. This process, called Fowler-Nordheim tunneling, allows devices to write and erase data quickly. Similarly, tunnel diodes, which rely on tunneling to conduct electricity, enable ultra-fast circuits used in high-frequency applications like satellite communications. While quantum tunneling offers incredible opportunities, it also presents challenges. As transistors in computer chips shrink to nanoscale sizes in electronics, tunneling becomes a problem. Electrons can tunnel through barriers they're supposed to stay behind, causing leakage currents that waste power and create errors. Engineers work hard to design materials and structures that minimize unwanted tunneling, while harnessing its benefits in devices like tunnel diodes. Tunneling also raises profound questions about the nature of reality. How can a particle pass through a barrier it shouldn't be able to cross? What does this tell us about the boundaries between the possible and the impossible? Some physicists see tunneling as a glimpse into the probabilistic nature of the universe, where nothing is ever truly specific. Others explore its role in theories like quantum cosmology, where tunneling might explain how the universe began. Quantum tunneling isn't just for scientists, it's a gateway to understanding the universe at its most fundamental level. This phenomenon shows us how the rules of the quantum world shape everything from the stars to the devices in our pockets. If you're curious, I encourage you to explore more. Read books like Quantum Mechanics, The Theoretical Minimum by Leonard Susskind, or watch lectures on quantum physics online. Follow experiments at places like CERN or the Perimeter Institute to see how tunneling continues to push the boundaries of discovery. The more you learn, the more you'll appreciate the hidden magic of the quantum world. Dive in and let your curiosity lead the way. What an amazing journey we've had today. We've explored what quantum tunneling is, from its mind-bending mechanics to its incredible impact on nature and technology. This phenomenon reminds us how strange and beautiful the universe is, and I hope it inspires you to keep exploring. What do you think? Does quantum tunneling fascinate you, or do you want to learn more? Share your thoughts in the comments. I read every one. Suggest topics for our next video, give us a like, and subscribe to stay curious with me. Thanks for watching, and I'll see you soon.